Imagine trying to write a complex novel, but every few words your pen mysteriously changes the letters, or the ink fades away. How could you ever finish your story accurately? This challenge is very similar to what quantum computers face with errors and noise. The Quantum Threshold Theorem states that fault-tolerant quantum computation is possible if the error rate of individual quantum operations is below a certain critical threshold. This means that if we can keep the errors on our quantum bits and gates small enough, we can effectively correct those errors and perform arbitrarily long and complex quantum computations without the errors accumulating and ruining the result. This theorem is incredibly important because it provides a theoretical lifeline for quantum computing. Quantum systems are inherently fragile, highly susceptible to environmental noise and decoherence, which can cause errors in their quantum states. Without a way to manage these errors, any quantum computation would quickly become corrupted and useless. The theorem confirms that despite this inherent fragility, we can theoretically build powerful, error-corrected quantum computers, provided we meet a specific quality standard for our hardware. For practical application, this means that the engineering goal for quantum computer developers is to build qubits and quantum gates with error rates that fall below this critical threshold. For example, many theoretical estimates for this threshold are around 1%, or even less for some architectures, meaning that more than 99% of quantum operations must be performed without error. Reaching this level of fidelity for every single operation is a monumental engineering challenge. An important aspect this theorem introduces is the concept of fault-tolerant quantum computing, often called FTQC. Achieving FTQC involves significant overhead costs, which means using many more physical qubits than logical qubits. A single logical qubit, which is error-corrected, might requiring hundreds or even thousands of physical qubits to encode its information and protect it from errors. This trade-off between error rate and resource overhead is a key consideration in designing future quantum processors. Ultimately, the quantum threshold theorem transforms the existential threat of quantum fragility into an achievable engineering problem. It assures us that, if we can make our quantum components sufficiently precise and reliable, then robust and powerful quantum computers are not just a theoretical dream, but a practical possibility. This insight guides global research efforts, focusing on improving qubit quality and developing ever more efficient error correction codes to navigate towards a truly useful quantum era.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.